Ever since Darwin, the idea that we humans evolved from an ancient ancestor who looked and acted much like a modern chimpanzee has been widely accepted. It seems to make sense that millions of years ago, there was some kind of transitional chimp-like species that walked on two legs instead of on all fours. Were the Ardi fossils from that creature? Clues from Ardi's pelvis might help answer this question. Early in the investigation, Lovejoy identified a distinctive clue on the intact front edge of Ardi's pelvis, a small feature with big implications. It was a shape common to all hominids, and was clear evidence that Ardipithecus didn't move on all fours, but walked upright on two legs. She was bipedal, like us. Following up on this early sign that Ardi was bipedal, the team cleaned and studied more of the badly broken pelvis. Separating the original fossil fragments and putting them back together by hand was out of the question. There were simply too many, and they were all too fragile to handle.
You're saying that that matrix felt cracked. When we opened that up, there's nothing in there.
Now, Lovejoy realizes he will need to make an accurate restoration of Ardi's pelvis. To do this, he'll use his knowledge of primate anatomy along with a cutting-edge technology called micro-CT scanning. Suwa's laboratory in Tokyo is one of the few in the world equipped for this task. In December of 2003, Suwa and Biene arrive at the University of Tokyo Museum with Ardi's fragile bones intact.
Okay. All right, one finished.
Using the museum CT scanner, Suwa will take 8 weeks to produce thousands of high-res scans of Ardi, the most comprehensive mapping of an ancient hominid skeleton ever attempted.
Relative to the beam and the detector is crucial.
The team wants to learn as much as possible about Ardi's skeleton. The scanner will allow them to study both the inside and the outside of each fossil bone and tooth. Here's one of Ardi's 4.4 million-year-old molars, seen from the surface and scanning down into the fossil tooth. Suwa will work 16-hour days to make thousands of these precision scans, pushing both himself and the technology to the limit.
Aspects of this specimen where the joint surfaces are relative to each other.
And now, 15 years after Ardi's pelvis was unearthed in Ethiopia, the scientists' long investigation is finally helping to answer the question of how this strange new hominid moved.
If I compare the pelvis of a chimpanzee to Ardipithecus's pelvis, what you see is a dramatic set of differences in all of the anatomical characters. This is the pelvis of an animal that locomoted bipedally. It just wasn't as highly evolved in doing so as was Lucy.
The pelvis reconstruction has confirmed that Ardipithecus was bipedal, a major step forward in the investigation. Another key part of Ardi's anatomy is her skull. An accurate reconstruction of the skull could provide the scientist with a number of insights, including the size of Ardi's brain. Once again, the original fossils in Africa are the starting point, and once again, the collaboration would span the globe. At Aramis, the team had recovered 34 separate pieces of Ardi's skull, including her jaws and teeth, but many parts were never found. In Tokyo, Suwa will reconstruct the Ardi skull using CT scans, filling in missing parts digitally. In Berkeley, California, White will also rebuild the Ardi skull, but to make his version, he'll use plaster casts of the fossils. Working this way, they're able to cross-check their results independently. Suwa scans the cranial fragments. Then he uses the CT slices to properly restore each bone. Front teeth are added, and the face of Ardipithecus begins to emerge. The digital reconstruction process would take years. Finally, a composite CD assembly is output from a computer as a 3D plastic version called a stereolith. Suwa sends it to Tim White in Berkeley.
So this restoration was accomplished digitally in Tokyo. This restoration was accomplished physically here in Berkeley. When we compare these two independent reconstructions, we're seeing effectively the same face.
The scientists have now reassembled the face of this enigmatic creature, seen for the first time in 4.4 million years. She had a very small brain, and yet her pelvis shows she walked bipedally. Ardi seems to have a foot in two worlds. What other secrets did the rest of her strange skeleton hold? Whether it's crossing a street or stepping down on the surface of the moon,
One small step for man.
we humans do it on 2 feet. In 1969, Neil Armstrong's footprints on the lunar surface became symbols of our scientific progress. 9 years later, the discovery of a series of fossilized footprints in Tanzania revealed that our ancient ancestors had made a giant leap of their own. What came to be known as the Laetoli footprints were made by members of Lucy's species. They established that hominids were already walking upright on human-like feet some 3.7 million years ago. But what about Ardi's feet? They're nearly 1 million years older than the Laetoli footprints. What could they tell us about the beginnings of bipedality? While cleaning the Ardipithecus skeleton, the scientists were stunned to see the shape of a bone near the center of Ardi's foot.
The real shocker was the medial cuneiform from the foot, because it told us that we had a grasping foot, just like you'd see in a chimpanzee.
This bizarre combination of a primitive, grasping big toe in the foot of a biped was unprecedented. The skeleton's curious mixture of primitive and derived traits revealed that Ardi was neither chimp nor human. She was an evolutionary mosaic. Ardi's chimp-like big toe was just one of the many surprises found during the investigation of her skeleton. Another would come from the bones that made up her hand. Ardi's hands were remarkably complete. Even tiny sesamoid bones that once rested within the tendons of her fingers were recovered. Did the earliest hominids, like Ardipithecus, evolve from ancestors who walked on their knuckles the way living chimpanzees do? Using Ardi's reassembled hand, the project scientists would now be able to test this hypothesis.